All right, folks, here we go. Wednesday, power, all that good stuff for us. So today we're going to talk through, like I said, power. So your big thing here is today, um, just make sure you watch through videos, try out some of these problems, all that good stuff like that. Okay. So we ask, what is this power thing anyway? Power is actually a pretty simple concept for us. Power is the work done at a certain so up until this point, we haven't been too concerned with how fast we get work done or how slow it takes us to do work. But in order to actually calculate power, that's where we need to know. All right, how fast is this taking place? All right. So power equals work over time. Another one to add to your list for today. All right. The unit for power is watts. Okay, so we ask, what is a watt? I know. Science, dad jokes, all together like that. It's horrific. I'm sorry. A watt is a joule per second. Okay. Now, yeah, we could go into more detail, more depth with how that joule is actually broken down into kilograms and meters and stuff like that, but we're not necessarily going to do that per se. So when we look at it being a joule per second, that's work, that's time. Now, the other thing we can do is we can really start to dig into other variations of this. So if you remember back when we talked about work and we talked about it being force times distance, if we use the Newton meters, now we allow ourselves to be able to calculate work a little differently. Okay, newtons is a force, meters is a distance, seconds is a time. So knowing those three different things, what we can do is we can take a force times a distance and divide it by a time, right? So we don't need to necessarily have the work perfect. We can do a force and a distance, right? We can also do a force and a velocity, right? So what we see here is that newtons is a force, meters per second is a velocity. So it gives us options as far as trying to actually calculate and see what a watt is. Okay? Now, watt is the standard unit of power, but watt isn't really big. What we'll find is we use kilowatts. And your house is going to measure actually kilowatt hours. So what Dakota Electric or what other electric service you have, I think Dakota Electric is pretty much synonymous here. You're going to see is that they have the ability to be able to measure how much power your household uses in that concept of a kilowatt hour. And that just becomes something that the industry starts to use. If you look at solar panels, as I walk around Lakeville, as I drive around Lakeville, they're becoming more and more prevalent, right? And yes, there are ways that people have put up enough solar panels and created their own grid that they can go offline, so to speak, meaning that they can go and power their own. If you produce enough solar electricity, guess what happens? You can put it back into the system and you get paid for that. Kind of crazy, right? So what we see here is that in 2018, when this graphic was made, a solar panel had become about 18 or 19% efficient, right? I don't know what it is today. I probably should have looked into that, but what that means is that it can produce 320 watts, 0.32 kilowatts, all right? So here's our formula list now. So if you need to pause this video, write down the bottom three, all right? What you'll notice as well is I have some could be's here, right? What that means is that you could write those different, meaning you could write work equals force times the change in distance as delta x, right? So on and so forth. So here was the first one we showed, right? Power equals work divided by time. Here was the second one. Power equals the force times the distance divided by time. Here was the third one. Power equals force times velocity. Yeah? Let's try it out. Let's give it a shot. Practice through it. All right. So how much power does it take a car to drive at a steady 30 meters per second if the car experiences a total resistance of 1400 newtons? Now, what we see here is we got 30 meters per second, we got 1400 newtons, right? So with that in mind, what we're able to see now is that we have a velocity and we have a force. So because we have a velocity, that velocity, as you can see, is going to go right into the back part here. Force is going to go right into the front part there, right? Multiply those two together, we find that that vehicle going at a steady about, what is that, 66, 67 miles an hour, should end up producing a power or needing a 42,000 watts of power, right? That's 42 kilowatts. It also turns into 56 horsepower. Now, please do not feel the need to know the relationship between kilowatts and horsepower, right? That's not something we have to memorize. It just gives you a reference point for this one to be able to say, oh, okay, 56 horsepower is this, all right? What that means is really horsepower is just how much strength our vehicles have, right? You can get, supercars that have huge amounts of horsepower, you can get small compact cars that have minimal amounts of horsepower, right? It just becomes another way for us as Americans of explaining how power works in a car, okay? Here is section 2 homework. I can't tell you enough how much I want you to do this today, right? Today or tomorrow. It likely will not take you an incredibly long time, just because once you hunt through and look for numbers, you should be able to find these. Now, yes, there's an additional problem on the tail end of this. It's about kinetic energy. Not super worried if you do that or don't do that. Okay. Otherwise, that's what I got for the day. I'll put out a pre-quiz as well today and tomorrow for you so that you can have that to look through if that's something of interest to you. Otherwise, that's notes for the day. Take care. All right. See you later. Bye-bye.